Okay, well, happy 10th week, everybody. And, oh, you know what? I forgot to do something. Okay, so this Friday, we will take our last test for this class. Sorry, I can't talk and type at the same time. Okay, so on Friday will be our last exam. It's technically our final exam, but I don't want you guys to think of it as the final. Just think of it as the third test because it's weighted the same as the other tests. It's 45 minutes, and I'm going to be nice to you, okay? So I still have to post homework 6, and that will be due a week from whenever I post it. So either I'm going to try to get it up by tonight, if not tomorrow. But I will also post another document at some point today, and basically I will. I already said I'm going to do this for the first class, so I can't take it back. I'm going to give you all the questions that are going to appear on the final exam. Okay, so. Yeah, it's not, well, okay. So I'll give you all the questions, okay? And they're all going to be kind of conceptual in nature, not a whole lot of like maybe 1 or 2 calculation-based questions, but the rest will all be kind of conceptual. And there will probably be like 15 questions in this document, okay? And you guys are allowed to, so it's not really a take-home exam because you're allowed to talk with each other and decide like what is the best and correct answer for this, okay? And then on Friday, you're just gonna write down your answers, okay? So this,
will there be on Friday?
huh?
Really like 5?
I don't know. Well, it's 45 minutes, so I figure you guys can write answers to, I don't know, probably like 10 questions or something. It's just short. They're short answer. They're gonna be conceptual things like. Yeah, don't laugh at. I think this is okay. So it'll be like one of them might be like, what's the point of Monte Carlo methods, right? Like, and what would you say? Okay, but why are we trying to get a random sample from the target distribution?
It's hard to get. That's hard to get.
Okay, all right. Well, you can improve your answer here. All right.
Okay. Wow.
So, well, I mean, because.
What would your answer?
Yeah, what would my answer be, right? Because I'll put down questions that I think are important that you walk away with. Okay, and then I have to link to this document. It's called Gibbs Sampling for the Uninitiated, and Dr. Resnick from the Department of Linguistics and the Institute for Advanced Computer Studies at University of Maryland wrote this. It's actually a very accessible article that is required reading for you guys, okay? So the first few pages just kind of covers the concepts of the Gibbs sampler, which I think I've tried to cover, and I hope so far it makes sense. And then but so far the examples we've done for the Gibbs sampler are like toy examples, right? Like the bivariate normal, which is already solved and simple enough to deal with. But this is an actual application that's very powerful. Gibbs sampling for the uninitiated, okay, and we'll go through it today, okay, and so homework 6 will deal with this, and I'll kind of cover all of that in a moment. Okay, are there any questions about how this final exam thing's going to work? The quote-unquote final exam, which is really just come to class and yeah. Yes, Lucas.
So you said like 15 questions. Will it be all 15 questions, or like?
No, I'm not. I don't think you'll have time to write your answers down for all 15 questions in 45 minutes. But there'll be 15 questions that I think are important enough, or I don't know. The pool might be just a tiny bit bigger or whatever, but they're kind of like questions that I think are going to be important that you should be able to answer, and that's it. Okay, and I hope that relieves a lot of stress and anxiety regarding the last exam, because it's spring quarter, right? You guys, a lot of you guys are graduating. Let's just get you out of here. Yes. What's that? No cheat sheet for the. Then it just becomes turning your homework. Yeah, that's silly. Okay. Yes.
Was it to get like parameter estimates for the distribution?
Oh, what's the whole point of Monte Carlo?
Go to tell us if it's okay.
Yeah. I would say the answer is to avoid hard math.
Right.
So usually there's some kind of question that might be for probability based, stochastic type of thing, and maybe there's hard math involved that we can't answer directly, and so we can get estimates of whatever we're looking at by having a large sample, a representative sample of whatever distribution we're looking at, and then and the Monte Carlo methods are all about how do we get that representative sample in order to answer the other questions. All right. Okay. If you will indulge me before I start today's lecture content and lecture material, I want to take a moment to recognize excellence. Okay. And so, if you guys have been on Piazza, I think there has been one student that has stood out above and beyond everyone, and maybe you didn't even realize that this was one of your fellow students, and you thought this was a TA or something. But Yizu Tan, I'd like to call you up here and just thank you for all the work you've done on Piazza. Huh? I got you this book. This is called The Book of Why. It's by Judea Pearl. He is a professor in the computer science department. He just published this book last month, and I went to the book release party, and I got a signed edition made out for you. All right, so this is the congratulations, or thank you very much. All right,
Should I put it on Piazza?
All right, but thank you for your work. So it's a very fascinating book. So I'm not buying everybody else signed copies, but anyway, the book is about causality. Okay, so throughout statistics we probably chant this mantra: correlation is not causation, and that is true. But Judea Pearl challenges that assertion and says, up until this point we haven't had mathematical models that allow for causal relationships, and so he proposes some new ways of kind of writing down probability models. So rather than just having given probabilities, we can talk about, or rather than just having conditional probabilities, we can have conditional probabilities where you forced a change. So what's the probability that the sun will rise if the rooster crows, or the sun is rising if you hear the rooster crow? So given that the rooster has crowed, what's the probability that the sun rises? That's high. Okay. However, if you're able to force a rooster to crow, that's not going to change the probability that the sun has risen. So he says you need to have a new notation that says what's the probability that the sun rises, given that you've forced a rooster to crow. And by having that distinction, you can now have math. But and that's like written for the general public, or at least a scientific public, and so it's not super heavy on the math. So anyway, a plug for a fellow UCLA professor's work. Okay, anyway, I am excited about today's topic, where we're going to take a look at the use of Gibbs sampling in the context of document classification, and we'll see how far we can get. It's a fairly involved model, so make sure you do your reading. So on Wednesday, when we continue on, this is where we're headed today. It'll all make sense. Okay. So we got Gibbs sampling for document classification. Okay, and today, as far so a document in this thing is going to be treated as a bag of words. Okay, there are many different models here, but here we're going to just treat the document as a bag of words. So you can imagine a cartoon illustration where all the words on the page just kind of fall down into a bag, and so the order in which we place the words is not part of our model. It's just what words appeared, how many words appeared, and we basically turn the document, which has structure and syntax and all of that, just into a bag of words. And we say, we see the word "the" appear 20 times, and the word "is" appear 15 times, and the word "good" appears 8 times, and the word "bad" appears once, and things like that. Okay, so we're going to turn the document into a bag of words, and then the classification is just based on the bag of words. Let's classify the document. Okay, and the application for this article is we're going to do a sentiment analysis. Okay, in that, and we're either going to try to say this has a positive sentiment or negative sentiment. Okay, so in our article, we have just 2 classes, positive and negative sentiment. Okay, but this could be extended. This same model could be extended into something that has more than 2 classes. Okay, so it could be, maybe you want to have some kind of way to go through a news website and classify the documents into, this is news about sports, and this is news about politics, and news about business, and I don't know, whatever else. Okay, you can have that, but for today's thing, we're just going to keep it simple, and we got 2 classes, either a positive or negative sentiment. And in fact, yeah, that's what we have. This is also going to be, we're going to start off unsupervised. Okay, we're not even going to say these documents are positively classified and these ones are negatively classified. We're just going to say, here's a bunch of documents. Let's see if you can kind of sort them into 2 groups. Okay, there's obvious shortcomings with kind of a bag of words model. Okay, because within the structure of our language, the arrangement of words can play a key role, right? And here we're just looking at how many times did this word appear, and and we base it off of that, right? So so for example, if somebody says this team is the greatest ever, yeah, right, okay, and they put this, there's like a tweet, right? It says the Cavs are the best team ever, yeah, right, okay, and we would recognize that is negative sentiment towards the Cavaliers, but the bag of words model would only see the words like best and yeah and right, and it would classify this as positive sentiment. Okay, so there's obvious shortcomings, but as far as a simple model goes, it's not too bad. Okay, so let's take a look, and we will say, okay, we're gonna say we have a corpus, okay, of documents, okay. So this is just going to be kind of the collection of everything, and then in that corpus, we have some document J. Okay, in document J, has label LJ, okay? And LJ can equal 0 or LJ can equal 1. And this is going to be basically the classification of document J. Okay, and we will say that the label LJ is drawn from a Bernoulli distribution with parameter pi. Okay, so pi is the probability that a document belongs, or the document has L sub j equal to 1. Okay. So the label comes from a Bernoulli distribution. Okay, and then and given a label Lj, we will generate kind of the words in our document. Okay, so I'll say associated with Lj equal to 0 is vector theta 0. Okay, or I should say associated with Lj equal to 0 is vector theta Lj, which is going to be set to theta 0. Okay, so because Lj is equal to 0. And then, we also have associated with Lj equal to 1 is vector theta Lj equal to theta 1. Okay, and theta 0 is a vector of probabilities for all the words I guess for all the words in the language. Okay, so maybe, I don't know, on the order of 50,000 words. Okay, so theta 0 is kind of just all the probabilities, and the sum of all of these theta zeros from I equals 1 to, say, 50,000, this will add up to 1, right? So it's just the word A has this probability of appearing, the word the has this probability of appearing, the word coconut has this probability of appearing, okay? So it feels at this point kind of like the lexical database, okay? However, it's different. It's as if you have one lexical database for positive sentiment and another lexical database for negative sentiment, okay? So it's we've gone through and we've adjusted some of these words and say, if somebody is in a good mood and they're speaking positively, then the probability of certain words are going to be higher, right? So in this thing, you'll have kind of your vector of probabilities, and then the word good will be higher than usual, okay? And the word bad will have a kind of a lower probability, et cetera, et cetera. And other words like amazing, will have higher probabilities, and so on and so forth, okay? So that everything still has to add up to 1. So as you adjust one and say we're going to increase the probability of this word, other probabilities have to go down to kind of make sure everything still adds up to 1. So you've got a vector theta 0 for kind of, well, whatever theta, if let's say theta 0 is positive, okay? I don't know, okay? And then so theta 1 is for negative sentiment. And again, theta 1 is a vector of probabilities for all the words. And you've got basically all of the vector sum is 1, and then over here, probably good will have a lower probability, and bad will have a higher probability, et cetera, okay? So on and so forth. So now we have these vectors theta, kind of showing the probability of each word, and saying, if someone is speaking positively, certain words are going to appear more frequently, other words will be less frequent, and then almost the opposite for negative words, okay? For negative sentiment. So we have the vectors theta, and then as far as the words themselves, okay, the document consists of kind of words and their counts. Which will be, so document WJ will be kind of the words and their counts. So this is a vector of the words and counts. Basically a vector of counts for each word. So it'll be like that. And this will be drawn from a multinomial distribution. Okay. And the multinomial distribution has kind of parameters Rj. This is going to be the number of words in document J. And then theta theta Lj, okay? And this is basically the word probability vector for the class LJ associated with document J. Okay, so if document J is a positive sentiment word, then the words that are drawn from the multinomial, or the counts drawn from the multinomial distribution, will be determined by the vector associated with positive sentiment, that probability vector. And then if you've got document J is negative, then the counts of the words are drawn from the multinomial distribution as determined by the probability vector for negative sentiment words. Okay, does that make sense? Okay, so that's kind of how our words, our documents are generated. But we'll have prior distributions on each of these things. Okay, so so we have LJ comes from a Bernoulli distribution with parameter pi, right? So the label, whether a document is a positive or negative word document, will be determined by by probability pi. And what would be the conjugate prior for the Bernoulli? So, okay, hint, Bernoulli is the exact same thing as binomial, but with just one draw, one sample, rather than n. Yes, the beta, okay. So pi would come from a beta distribution, okay? So the conjugate prior for the binomial is beta, and naturally the conjugate prior for the Bernoulli would be beta. Okay, and we're gonna so the beta normally has so beta would have two shaped parameters, an alpha and a beta. To kind of follow the notation here, we're gonna have gamma pi. What is the letter they use here? Gamma pi 0 and gamma pi 1 to signify shaped parameters 1 and 2, and we're just going to collect these into the vector gamma pi. Is that okay? So the beta distribution, like in all of my past lectures, I've said are determined by shape parameters a and b, or alpha and beta. To the notation in this article is they're using gamma pi 0 and gamma pi 1, and they actually collect both of those into just a vector gamma pi to represent those two values. Is that okay? And then we said the word counts, WJ, come from a multinomial with RJ and theta. Okay, and we will say theta itself, so whether it's theta 0 or theta 1, the conjugate prior for a multinomial is called the Dirichlet distribution. Okay, and the Dirichlet distribution has prior kind of gamma, vector gamma theta. Okay, and so so the beta distribution varies from 0 to 1, and I don't know, maybe it looks like this, right? And it says, you know, some value, the probability that the coin lands heads is going to be some value between 0 and 1, something like that. Okay, the Dirichlet distribution is basically a multi-dimensional generalization of the beta. Okay, so imagine having I don't know, sounds like it's like stuck in that vent right there. Okay, imagine having like a cube, Okay, maybe not a cube because that implies all 6 sides are equally sized. So you've got some polyhedron, is that what we would call it? Okay, you've got some polyhedron, you're going to roll this thing, and you want to say, what's the probability of each side landing, right? And so that might, the probability of each side has to be between 0 and 1, okay? But you've got more than 2 sides. So now you might have like 6 sides, okay? A 6-sided polyhedron. And so basically each side will be between 0 and 1, okay? And obviously because everything has to add up to 1, you know, it'll probably look something like this. This is going to be for side 1, and you got 0 and 1, and it'll be like this for side 2, and so on and so forth. And you've got basically all of these like little, almost like beta distributions, but you've got them for every single side. Okay, technically, if you have a 6-sided polyhedron, you would have distributions for 5 of the sides, because the 6th side doesn't have any degree of freedom there, and because it has to, all sides have to add up, all the probabilities of all the sides have to add up to 1. So once the first 5 have been determined, you no longer, you got sides minus 1 degrees of freedom. So anyway, that vector theta comes from a Dirichlet. So it's just a multi-dimensional generalization of the beta. So the beta varies from 0 to 1. The Dirichlet will generate a vector where each of the values in that vector vary from 0 to 1. Okay. Is that right? This concept of a Dirichlet distribution? Okay, and so, you know, so when we are generating theta, technically this would be for like all, 50,000 or 80,000 or however many words we want to include in our model of the English language, right? So, and we would say the probabilities over, all of these things for the positive sentiment is something like that. Eventually you're going to code this up in your homework, okay? That's what homework 6 is. But to kind of keep it simple, so you don't have to have a vector of 50,000 words, you're still doing document classification, but we're going to keep it to kind of a small vocabulary here. And so I'm using 2 children's books, okay? One is Green Eggs and Ham, okay? And by Dr. Seuss, Theo Geisel, and I don't know if you guys know the story, or I don't know, maybe this is just the legend of how Dr. Seuss wrote Green Eggs and Ham. So a friend challenged Dr. Seuss, I bet you can't write a book with only 50 words, and he did it, right? He wrote Green Eggs and Ham, and there's basically only like 50 unique words in the entire book, because there's just a lot of repetition, right? Like, I will not eat them with a fox. I will not eat them in a box. Stuff like that, and it's just the same words repeated. So you have that, and then I have another book, children's book, Go Dog Go, and that's just about dogs. Yellow dogs and green dogs and black and white dogs and big dogs and little dogs, and basically I've taken the text of the entire book, and I've cut them up into like 2-sentence quote documents, okay? And the idea is, if I show you 2 lines, can you figure out which book this came from, right? So you still want to take the this mini document, and you want to classify it. Did it come from Green Eggs and Ham, or did it come from Go Dog Go? Okay, as a person, this is a very easy task for you guys to do, right? You see the word dog in there, and you go, oh, it's going to come from the, well, I don't know. So you do that, okay? But the question is, can we still give the computer a bunch of unlabeled documents, either that just consist of kind of words, and can the computer group them together, okay? And we're not giving it labels. We're not saying, some of these are coming from go.go and some of these are coming from green eggs and ham. We're just saying, here's a bunch of stuff, sort these out. And if, obviously, well, not obviously, but if we can get it to work for kind of this toy case of the 2 children's books, with enough computing power, you can use a similar method to try to classify positive and negative sentiment tweets or whatever it is that we're looking at. Okay, so these are our prior distributions, and what we want to do now is we want to create the entire joint distribution. Okay, and so there are a few more variables that appear. So we've seen L and theta and pi and gamma, this and that. Okay, so a few more variables. So this C, this represents the corpus of all the documents. And we've got C0 or C1. This will be the corpus of documents labeled 0 or labeled 1. Okay, and then we'll also have, during the sampler, this will be all the documents, the corpus of documents, all the documents except document J. Okay, all the documents except document J. Okay, let me also draw a plate diagram showing our model. And this is this also appears in our document or the article. And so you have gamma pi. This is kind of the prior hyperparameters for the prior distribution. Hyperparameters for the prior distribution of pi. Okay, so this is a beta distribution. And from that, via beta distribution, we get pi. And so pi is going to be the probability that a document belongs to class 0 or 1. Okay, so this is a kind of we use a beta distribution to generate this. And from that, we use a Bernoulli distribution to get the label LJ. Label of document J. Okay, and this is going to appear. This happens for all J documents. Okay, for all N documents. Okay, so this plate represents for each of the N documents. Okay. Meanwhile, we've got another prior vector, gamma of theta. This is the kind of the prior for the theta vector, which is the probability over all the words. And from there we draw theta. Okay. And there's two of these, okay? We have theta 0 and theta 1. Okay? Because we've got a different theta for each class of document. Okay? And based on that theta and which label it is, okay, this will generate our our word count. Okay? And this happens, so we generate, how many times did word K appear? The word good appeared 3 times. That's going to be, the value for, the word good appeared 3 times in document J. The word bad appeared 0 times in document J. The word amazing appeared 5 times in document J, okay? And, we would probably say, well, J is probably a positive sentiment thing, okay? And so there's a total of RJ words in document J. Okay, and so this is our plate diagram for our kind of document generation here. Is this okay? All right, and so the joint distribution for the entire document collection probability of kind of the corpus, the all of the document labels, the value pi itself. So the corpus is kind of, it would be the matrix of all the document counts for, all the word counts for every single document. Okay, so so this is like a matrix. You stick all the W vectors together into a matrix, and you get the corpus. Okay. The document labels, the probabilities, the probability of label whatever, pi, and then the vector theta 0 and the vector theta 1, okay? Given the parameters, so the semicolon is given the parameters. Vertical bar is given random variable is equal to something, and this is still given a random value variable, but here we're going to have the parameters kind of the hyperparameters, gamma pi 0, gamma pi 1, and gamma theta. Okay, and this we can decompose to, okay, and we'll take this entire joint distribution and we're going to split it up into the different pieces. We've got pi is determined by the values gamma pi 1 and gamma pi 0. Okay, and once you have pi determined, then you've got, so this is the beta distribution of getting pi. Okay, and then you've got L given pi, and this is what is this distribution here? This is the Bernoulli distribution of getting L from pi. Okay, but a product of kind of Bernoulli draws. Then you've got theta 0. These are vectors. Okay, theta 0 given. So this is a Dirichlet distribution. And so is this. So you've got theta 0 and theta 1 kind of drawn from these Dirichlet distributions. Dirichlet distribution of getting the word vector, getting the word probability vector, theta 0 or theta 1. Okay. And what else do we have left? Oh, we've got to have then the corpus of positive sentiment documents given the vector of positive word probabilities and basically the documents that are labeled positive. Okay. And then the kind of the corpus of negative sentiment words, or things classified, and these are kind of basically multinomial draws based on the probability vector theta. Yeah, probability vector theta. Okay. And this would be kind of this entire joint probability of all of the things, and we've kind of factored them out into these things, and we're trying to get us set up to use the Gibbs sampler, which uses conditional distributions on each of these things. All right, is this okay? Okay, we're out of time, so make sure you do the reading of the article, because that will help. We'll finish this out on Wednesday, and then you'll code it up for your homework. So make sure you do the reading. I think that'll help in understanding your Wednesday.